population is a complete group of people, animals, things, or places that have something in common with each other. If you ask a person to think of an example of a population, the person will probably think of a group of people that all live in the same area. For example, the person might think of the population of people living in San Jose, the population of people living in California, or the population of people living in the United States. However, a population doesn't have to be a group of people that all live in the same area. Any group of people that have something in common are a population, and living in the same area is just one thing that a group of people could have in common with each other. All people living in San Jose are a population, but so are all people who own cell phones and all people who run Facebook. All people living in San Jose are a population because they have something in common with each other. What they have in common is that they all live in the same city. All people who own cell phones are a population because they have something in common. What they have in common is that they all own the same product. All people who run Facebook are a population because they have something in common. What they have in common is that they're all on the same social network. The words complete group are important in the definition of a population. A population is a complete group or a complete collection of people, animals, things, or places without any members being left out. If you're driving and you see a city limit sign, you'll notice that the city limit sign has a number on it that shows the number of people in the population of the city. In order for that number to be showing the exact size of the city's population, that number has to include every person who lives in the city. If even one person is left out, that number isn't actually showing the exact size of the city's population. What this means is that if a city wants its city limit sign to be showing the exact size of the city's population, the city has to change the number on the sign every time a person moves into the city and every time a person moves out of the city. If a city wants its city limit sign to be showing the exact size of the city's population, the number on the sign has to go up by 1 every time a person moves into the city and has to go down by 1 every time a person moves out of the city. Here's another example. All of the employees who work at a certain company are a population of employees. If I'm looking at a photograph that shows all of the employees who work at a certain company, then I'm looking at a photograph of the population of employees who work at that company. However, if even one employee is missing from the picture, then I'm not looking at a photograph of the population of employees who work at that company. If even one employee is missing from the picture, then I'm actually only looking at a photograph of a part of the population of employees who work at that company. What are some other examples of populations of people? All 4,312 people who work for the federal government are a population. All 20,642,819 people attending colleges in the U.S. are a population. All 1,369,532 people in the U.S. military are a population. We need to remember that a population doesn't have to be a population of people. A population could be a population of animals, things, or places. All mountain lions in the Bay Area are a population of animals. All red cars are a population of things. All $5 bills are also a population of things. All universities in the United States are a population of places. And all 50 states in the US are also a population of places. Populations can overlap. For example, college students who are on Facebook are members of both the college student population and the Facebook user population. Also, a population can fit inside of a larger population. For example, the population of people living in California is inside of the population of people living in the United States. Why is the idea of a population important? It's important because the purpose of collecting data is usually to learn something about an entire population. For example, a person who asks 100 college students how many text messages they send each week probably isn't only interested in the amount of text messaging being done by those 100 people. The person is probably asking those 100 college students how many text messages they send each week to get a rough idea of the amount of text messaging being done by college students in general. In general, if you collect data from a larger number of population members, you will get more accurate information about the population than if you collected data from a smaller number of population members. In a perfect world, a researcher would always collect data from every member of the population that he or she is studying. If you collect data from every member of the population you are studying, you will be able to get perfectly accurate information about the population you were studying, as long as all of the data was recorded correctly. As long as all of the data was recorded correctly, you'd be able to make perfectly accurate conclusions about the population you were studying. For example, if I was interested in the amount of text messaging being done by college students in the US, and I asked all 20,642,819 college students in the US how many text messages they send each week, I could use my data set to actually calculate the exact average amount of text messaging being done by college students in the US. I could calculate that average, or mean, by adding the 20,642,819 answers and dividing the total by 20,642,819. The number that I would be calculating in this case would be called a population mean. A population mean is a mean of an entire population. It's a mean, or an average, that describes something about an entire population. The problem is that most populations that people study are so large that it isn't possible to collect data from all members of a population, either because it's too expensive, too time-consuming, or not possible because some population members can't be reached or can't be contacted. What a researcher will almost always do is select a certain number of population members and then collect data from those selected population members only. The group of selected population members that the researcher collects data from is called a sample of the population. Let's think of some examples of samples. If I ask 100 college students to tell me how many text messages they send each week, then those 100 college students are my sample. They are the 100 college students who are providing me with data. If I ask 200 of the 4,312 people who work for the federal government to tell me how much money they make per year, then those 200 federal government employees are my sample of the federal government employee population. They are the 200 people that I'm collecting data from. If I go to a forest and I measure the heights of 300 trees, then those 300 trees are a sample of the population of trees in that forest. They are my sample of 300 trees because they are the 300 trees that I am collecting data from. The number of population members that are included in the sample is called the sample size. In my first example, in which I was asking 100 college students how many text messages they send each week, my sample size was 100. In my example in which I was asking 200 federal government employees how much money they are making per year, my sample size was 200. In my example in which I was recording the heights of 300 trees in a forest, my sample size was 300. In my first example, my sample size was 100 because I was collecting data from 100 college students. In my second example, my sample size was 200 since I was collecting data from 200 federal government employees. In my third example, my sample size was 300 since I was collecting data from 300 trees. In each of my three examples, the sample was the batch of people or the batch of things that I was collecting data from, and the sample size was the number of people or the number of things that I was collecting data from. In my first example, the sample was the 100 college students that I was collecting data from, and the sample size was 100. In the second example, the sample was the 200 federal government employees that I was collecting data from, and the sample size was 200. In the third example, the sample was the 300 trees that I was collecting data from, and the sample size was 300. Now we will talk about how a researcher decides which members of the population will be in his or her sample. There are different ways to select a sample from a population. You can select a sample by using random sampling or non-random sampling. Random sampling and non-random sampling are the names of two major types of sampling methods. If you use random sampling, then you are selecting members of the population randomly, and everyone in the population has an equal chance of being selected to be in the sample. Random sampling has to involve some type of lottery system that gives every person or animal or thing in the population an equal chance of being selected to be in the sample. If you write the name of each population member on a piece of paper, put all of the names into a hat, and then pull out names without looking, then you are using random sampling. You are selecting people randomly, and every population member has the same chance of being selected. In order for it to be truly random, it would be important to shake up the hat before you take out a piece of paper or before you start selecting people. Using this type of lottery system is difficult to do because you need to have a list of the names of all members of the population, and you need to have contact information for all members of the population if you're studying people. If you don't have a complete list of population members, then not everyone in the population will have an equal chance of being selected. For example, if you're studying people, then the people who are not on your list of population members will have a 0 chance of being selected. Also, if you don't have contact information for all of the people in the population you are studying, then not everyone has an equal chance of being selected because some of the members can't be contacted. Whoever you can't contact has a 0 chance of being selected. If certain population members are missing from your list of population members, or if their contact information is missing, then your sampling strategy is technically not purely random. Random sampling is supposed to give each population member an equal chance of being selected to be in the sample. The only way to give each population member an equal chance of being selected is to have a complete list of population members and to have a complete list of their contact information. The list of all population members that a researcher needs to have in order to select a random sample from a population actually has a name. It's called a sampling frame. A sampling frame is a list of all members of a population. A sampling frame also has to include the contact information of each member of the population. The opposite of random sampling is non-random sampling. In non-random sampling, you don't select people randomly. You either select the population members that you would like to include in your sample, or you let people who say that they would like to be in your sample be in your sample. If you use non-random sampling, then not everyone in the population has an equal chance of being selected. If I am walking up to people in a public location, such as at a college campus, and asking people to take a survey, then I am using non-random sampling. It might seem random, but it is actually not random because not everyone has the same chance of being selected. I am probably going to ask people who seem more friendly or who look like they would be more willing to take my survey. I'm probably not going to ask other people who look less friendly or who look like they would be less willing to take my survey. Also, if I put out an advertisement that says that I need people who are willing to take a survey, then I'm using non-random sampling because not everyone has an equal chance of being selected. Only the people who read the advertisement and are interested enough to contact me will be included in my sample. Random sampling is sometimes called probability sampling, and non-random sampling is sometimes called non-probability sampling. The reason why these terms are used is because random sampling gives all population members an equal chance of being selected, and non-random sampling does not give all population members an equal chance of being selected. The purpose of collecting data from a sample is to learn about the entire population from which the sample was selected. It is like how the purpose of eating a sample of food at Costco is to learn about the entire product. A sample can provide fairly accurate information about a population. However, a sample generally won't provide perfect information about the entire population. The only way to get perfectly accurate information about an entire population is to collect data from all members of the population. Let's imagine that I'm interested in the average GPA of college students in the US. Let's say that I ask a sample of 200 college students who live in the US to tell me their GPAs, and then I calculate the average of their 200 answers. I do this by adding up their 200 answers and dividing the total by 200. The number that I calculate with my data set might end up being close to the average GPA of the entire US college student population, but it is highly unlikely to be exactly the same as the average GPA of the entire US college student population. The number that I'm calculating by adding up the GPAs of the 200 people in my sample and dividing the total by 200 is called a sample mean. The number that I would get if I was able to add up the GPAs of all 20,642,819 college students in the US and then dividing the total by 20,642,819 would be called a population mean. The purpose of calculating a sample mean is to estimate or to get a rough idea of what the population mean equals. The mean of a sample is highly unlikely to be exactly the same as the mean of the entire population. However, the mean of a sample is often close to the mean of the entire population. That's why the mean of a sample can be used to estimate or to get a rough idea of what the mean of the entire population equals. Let's talk about two basic ways in which data from a sample can be used to learn something about an entire population. You can calculate the mean, or the average of a sample, to estimate the mean, or the average of an entire population. We just talked about an example of how that could be done. You can also calculate the percentage of something in a sample to estimate what the percentage would equal in the entire population. In other words, you can calculate the percentage of something in a sample to get a rough idea of what the percentage would equal in the entire population. I might find a sample of 200 college students who live in the US and then ask each person in the sample, "Do you live with your parents?" I could then calculate the percentage of people in my sample who said that they live with their parents. For example, if 100 out of the 200 college students in my sample tell me that they live with their parents, then 50% of my sample is saying that they live with their parents. This percentage could give me a rough idea of the percentage of all college students in the US who live with their parents. I know that just because the percentage of people who live with their parents in my sample was 50%, that doesn't necessarily mean that 50% of all college students who live in the US live with their parents. However, this percentage of 50% that I calculated can hopefully give me a rough idea of what percentage of US college students live with their parents. If the value that is being calculated with the sample comes out close to the value that's being estimated in the entire population that the sample came from, then the sample is providing the researcher with highly accurate information about the entire population. For example, if the sample mean comes out close to the population mean, then the sample mean is providing highly accurate information about the population mean. If the sample percentage comes out close to the population percentage, then the sample percentage is providing highly accurate information about the population percentage. If you want your sample to provide highly accurate information about the entire population, you're going to want a wide variety of population members in your sample. For example, if I was recording the ages of 200 college students who live in the US to estimate the mean age of all college students who are living in the US, then I wouldn't want to have a sample that's mostly freshmen and not very many other grade levels, because then the mean of my sample would underestimate the mean age of the entire population. I also wouldn't want a sample that's made up of mostly seniors and not very many other grade levels, because then the mean age of my sample would overestimate the mean age of the entire US college student population. What I would want is a balanced mixture of all four grade levels in my sample, so that the mean of my sample would come out fairly close to the mean of the entire population. I said that you can't depend on a sample to provide you with perfectly accurate information about an entire population. However, there are things that you can do to increase the chance that your sample will provide you with highly accurate information about the entire population. First, Larger samples tend to provide more accurate information about the entire population than smaller samples. The reason why larger samples tend to provide more accurate information about the entire population is because they tend to include a wider variety of population members. Smaller samples tend to give you too many of certain types of population members and too few of other types of population members. The reason why smaller samples tend to include a smaller variety of population members and why larger samples tend to include a wider variety of population members is because larger samples are a larger piece of the population. In other words, larger samples are closer to actually being the entire population. So when you collect data from a larger sample, you're more likely to come across a wide variety of population members. Just like how larger samples tend to include a wider variety of population members than smaller samples, random samples, meaning samples that are selected randomly, tend to include a wider variety of population members than non-random samples, meaning samples that are selected non-randomly. The reason why is because when a researcher does non-random sampling, the researcher tends to select people based on convenience. In other words, when a researcher does non-random sampling, the researcher often selects people from one convenient location. For example, a researcher doing non-random sampling might select a group of students who are all taking a class together, or a group of students who are all in the same building together on a certain college campus. And when you select people from one convenient location, you tend to get a group of people who are fairly similar to each other. Here's an example. If I'm teaching a psychology class and I need a sample of participants to take my survey, and I recruit the students who are in my psychology class, I've non-randomly selected a group of students who are at one convenient location, which is my classroom, and all of the students in my class are psychology majors, and since they're all taking the same class together, they're likely to be mostly all one grade level. For example, if I'm teaching a junior level class, my class will be mostly juniors. So by doing non-random sampling and by selecting people from one convenient location, I haven't selected a sample with a wide variety of population members. Now, if I had gone out and randomly selected people from the population, I would have ended up with a wider variety of people. I probably wouldn't have ended up with all psychology majors or all juniors. If I had randomly selected a sample, I probably would have ended up with a wide variety of different majors or a wide variety of different grade levels. What I wrote on the board is a summary of what we just talked about. I said that you want to have a wide variety of people in your sample so that you'll get accurate information about the entire population. The reason why you want to have a wide variety of people is because you technically want to have something called a representative sample. A representative sample is a sample that has the same mixture of people as the entire population. The opposite of a representative sample is a non-representative sample that doesn't have the same mixture of different types of people as the entire population. A non-representative sample is a sample that has too many of some types of people and too few of other types of people. Let's go through an example to help explain the meaning of a representative sample. Let's imagine that there's a population of college students in which 40% of the students live with their parents, and 60% of the students do not live with their parents. Let's also say that 20% of the students are freshmen, 30% of the students are sophomores, 20% of the students are juniors, and 30% of the students are seniors. I want to select a sample of 100 students from this population so that I can collect data from those 100 students. perfectly representative sample would be a sample in which the percentages of people in the sample match the percentages of people in the entire population. In order for my sample to be perfectly representative, I would need to have a sample in which 40% of the students live with their parents and 60% of the students do not live with their parents. I would also need to have a sample in which 20% of the students are freshmen, 30% of the students are sophomores, 20% of the students are juniors, and 30% of the students are seniors. Since I am selecting a sample of 100 students, a perfectly representative sample would include 40 students who live with their parents and 60 students who do not live with their parents. A perfectly representative sample would also include 20 freshmen, 30 sophomores, 20 juniors, and 30 seniors. If I ended up with that sample of 100 students, then my sample would be perfectly representative. Well, it would be perfectly representative, at least, in terms of living situation and grade level. We haven't checked other types of things like gender to see if gender is representative. I added what we just talked about to my summary on the slide. The reason why having a wider variety of people in your sample leads to more accurate information about the entire population is because having a wider variety of population members in your sample leads to a more representative sample. The reason why having less variety of population members in your sample leads to less accurate information about the entire population is because having less variety in your sample leads to a less representative sample. So representativeness is what you really want. You want to have a representative sample to get accurate information about the entire population. But in actual research, no sample is perfectly representative. So the best you can hope for is a fairly representative sample. You want to have a good chance of getting a sample that's at least fairly representative so that you have a good chance of getting fairly accurate information about the entire population. This is an analogy of why a representative sample is needed to make an accurate conclusion about an entire population. This cake right here is meant to be an entire population of food. The population of food has 3 layers in this case. It has a layer of icing, a layer of plain cake, and a layer of chocolate cake. We can see that each layer is a third of the cake. I want to take a sample of this cake so I can get an idea of what this cake tastes like. If I cut straight down, like this, then I'll end up with a sample that's 1/3 icing, 1/3 plain, and 1/3 chocolate, just like how the entire cake is 1/3 icing, 1/3 plain, and 1/3 chocolate. Since the fractions in my sample match the fractions in the entire population, my sample over here is representative. This sample right here is representative of the entire cake. And this sample right here would give me a very accurate idea of what the entire cake tastes like. After I eat the sample, I'll know that the cake is 1/3 icing, 1/3 plain, and 1/3 chocolate. So this is a representative sample. And it gives me highly accurate information about the entire population. What if I took a non-representative or a biased sample of the cake? What if I cut diagonally like this? And then this was my sample of the cake right here. This piece of cake right here obviously isn't a representative sample because it's more than 1/3 icing. It looks like it's probably more than 1/3 plain, and it's less than 1/3 chocolate. So the fractions in the sample don't match the fractions in the entire population. And since this sample of cake isn't representative, it's going to give me misleading information about the entire cake. It's going to make me think that the cake is mostly plain and mostly icing and not very much chocolate. So if I like chocolate, then this non-representative sample is going to make me think that the cake isn't very good when the cake is actually better than I think it is. This non-representative sample would lead me to a wrong conclusion about the entire cake.
One last point that I wanted to make is that even though random samples tend to be more representative than non-random samples, a representative sample isn't the same thing as a random sample, so that the terms random sample and representative sample have different meanings. So here's my last point. The term random sample describes a sample that's selected with a certain sampling method. There's a certain sampling method called random sampling, in which the participants are selected randomly, and when you use that sampling method, the sample that you end up getting is called a random sample. So this is named after a sampling method. But the word representative doesn't describe, or it doesn't refer to a certain sampling method. The word representative only describes the quality of the sample. So a representative sample is a high quality sample, and a non-representative sample is a low quality sample. But if a sample is representative, that doesn't necessarily mean that a certain sampling method was used. It only means that the sample is a high quality sample. Here's an analogy. Let's think about the terms um, bottled water and, I guess, river water. Both of these terms are named after a certain way of gathering water. Or, if water comes from a bottle, then it's bottled water. If water comes from a river, then it's river water. So both of these words describe where the water is coming from. And bottled water is probably more likely to be pure water than river water. So bottled water is more likely to be pure water. And river water is less likely to be pure water. So the word pure water, the word pure describes the quality of the water, just like how the word representative describes the quality of the sample. And just because water is pure doesn't necessarily mean it had to come from a certain place. Pure water doesn't have to necessarily come from a bottle, because there could be different ways of getting pure water. For example, if you use a filter, then you have pure water. So the word pure only describes the quality of the water, not where it came from. So this is how the water was, we could say how the water was gathered. These two terms talk about how the water was gathered, and this term of pure water talks about the quality of the water. Now down here, let's write out random samples tend to be representative samples. And non-random samples tend to be non-representative samples, or tend to be less representative. Random samples tend to be more representative, and non-random samples tend to be less representative, because no sample is completely representative. These terms, random and non-random, describe how the sample was gathered, how the people were selected. And the term representative describes the quality of the sample. So the words random and non-random describe how the sample was gathered, just like how the words bottled and river describe how the water was gathered, and the word representative and the word non-representative describe the quality of the sample, just like how the words pure and non-pure describe the quality of the water.